Bismillahirrahmanirrahim. Assalamu alaikum. I'm Fakhr Lodi and this is our 31st lecture of Formal Methods for Software Engineering. Remember, we have been discussing algebraic specifications. And in the previous lectures, we discussed the general structure of algebraic specifications and how can we specify abstract data types using algebraic specifications. So we saw the general structure of that, and then we saw a family of algebraic specification languages known as the large family of specification languages. In the large family of specification languages, remember that we had a language independent component where we specify the behavior of the abstract data type independent of a particular implementation language, and then we can refine those specifications using the language specific components for different languages. So we have those components built or designed for languages like C, Java, and so on and so forth. Today we shall start discussing another family of algebraic specification languages known as the OBJ family of algebraic specification languages. This once again is a family of languages, just like large is a family of languages, but in this particular case, this family of languages is very different from what we saw in the case of large. Large, the family of languages depending upon the implementation languages. Here we have these specifications which are independent of the implementation languages, but there is this evolution and different dialects and different versions of OBJ that we have, and those different OBJ versions, they are commonly known as the OBJ family of specification languages. The work on these specification languages started in the mid-70s, and the first one of these languages was OBJ0, and then we had OBJ1, and then OBJ2 and OBJ3. So the first generation of these languages, that is OBJ0, 1, 2, and 3, these were kind of evolutionary steps in the original OBJ language. Then we had the offshoots of this OBJ specification language, and there are other features that were added to this. And other dialects, other languages in the family include BOBJ, and the most famous one of these is known as Cafe OBJ. So we shall be discussing OBJ in general, and then we will take some examples from OBJ3, which is basically the OBJ, kind of a standard OBJ that we have, and then we will look into that Cafe OBJ. Cafe OBJ has been developed in Japan and has been quite successful in specification of complex systems. So this is what an overall overview of this OBJ family of languages is. The OBJ family of languages, they are based upon what is called as sort order algebra, or in short SOA. We shall see what is a sort order algebra in more detail, but sort order algebra lets us work with partial sorts. It is very, very difficult to give a complete definition of a data type or an abstract data type, so we can work with partial groups, partial sorts, and that lets us define and handle partial sorts with the help of exceptions, inheritance, parameterizations, and so on and so forth. So this sort order algebra is the fundamental concept which we use in OBJ specification languages. These specification languages, they influenced the design of many programming languages. The concept of module came from these languages, although we had the concept of kind of module in the case of Simula programming language, but the languages like C++ and so on and so forth, Ada, Modula, they were influenced by this OBJ specification languages. And the concept of a module, in the case of C++, this module is called a class. In the case of Ada, this thing called a package. The concept of this module or the implementation of these things in these specification languages or in these programming languages has been greatly influenced by the OBJ specification languages. So the OBJ specification languages, they have played a very significant role in the overall development of programming languages and software engineering in general. So we shall see what these languages are all about, and we will see a few examples of these languages. So let me take you to the slides to start talking about these languages. First, we look at some definitions, some basic characteristics, and then we will elaborate those characteristics. So let me take you to the slide. OBJ is a first-order functional language. It is based on equational logic, and we shall talk about equational logic. It supports parameterized programming. It supports declarative style that facilitates verification and allows OBJ to be used as theorem prover. We can include Lisp code in OBJ specifications, and it provides a flexible environment which is convenient for specification and rapid prototyping. So a couple of things here before we start discussing those in more detail. It is first order logic. That is probably most of the specification languages, they are based upon first order logic. Then we use equational logic in this particular case. What is equational logic? We shall talk about that in more detail, but the basic idea behind equational logic is that we substitute equals for equals. Remember, we discussed substitution of equals for equals in our very early discussions when we were talking about predicate calculus and the Hor's logic. In those cases, we discussed the role of equational logic. But the OBJ family depends very heavily, the specifications that we write in this class of languages depends very heavily on equational logic. I mentioned sort order algebra. We shall be talking about that later on in more detail. Another very important point here is that it mixes two styles here. It's a declarative specification language. So declarative means that we specify what, and if you are familiar with programming languages like Prolog, Prolog is a declarative programming language. In that particular case, we simply specify what, we do not specify the algorithm, so we specify it as a mathematical entity, as a declarative statement. Another more familiar declarative programming language that people use commonly, although the style is very different, but it is still a declarative programming language, is our SQL, the database query language, SQL. That is also declarative, but this OBJ style is closer to Prolog declarative style as compared to SQL. Another very important feature of this language is that we can add executable Lisp code in the specification. So, like I mentioned earlier, it combines two paradigms. One is the declarative style specifications, and the other one is the functional style programming. Remember, Lisp is a functional programming language. So this OBJ is a mixture of functional plus declarative style of languages. So we have executable code in this language also. So these specifications can be executed, and we can actually execute and see the results of this specification language. So this is a very powerful feature that gives us a very powerful, flexible environment in which we can not only specify the behavior of the system, but we can also build prototypes very quickly. So it is also a rapid prototyping language. So it is a multi-purpose kind of thing. Declarative style for specifying the behavior, functional style for execution, although we can also execute the declarative specifications. The execution engine is already there, so it will work very, very similar to how we execute a Prolog program. But at the same time, since it is executable, that means we can build prototypes with this specification language. Now, let us go back once again onto the slide and look at some of these concepts in more detail. Let us first look at what is meant by equational calculus. Equational calculus is a calculus of replacing terms by equal terms. Equational calculus derives or proves a term equation from a conditional equation axiom set. The deduction rules in this calculus are: number one, reflexivity. Any term is provable equal to itself, that is, t is equal to t. Transitivity. If t is provably equal to t2 and t2 is provably equal to t3, then t1 is provably equal to t3. So this is the transitive property. Then symmetry. If t1 is provably equal to t2, then t2 is provably equal to t1. And finally, congruence. If t1 is provably equal to t2, then any two terms are provably equal which consist of some context built around t1 and t2. So equational calculus, very simply replacing or equating equals with equals. So in equational calculus, there are four basic fundamental rules. These four fundamental rules are, first of all, it is reflexive. That is, a term is equal to itself. It is transitive. That means if a term is equal to another term and that term is equal to yet another term, that means the first term is equal to the third term. So very simple transitive rules. The third one is symmetric. That is, if term 1 is equal to term 2, then term 2 is equal to term 1. So that means they can be placed on either side of the equation. And finally, we have the congruence. We say if two terms t1 and t2, they are equal, then they can be replaced by each other whenever they come in a particular context. So nothing very special here. All we are saying is we can replace equals with equals, and the properties are that it is reflexive, it is transitive, and it is symmetric. And we can, congruence automatically comes from there. Remember the three properties, that is reflexive, transitive, and symmetric. If you go back to your discrete mathematics, you will remember these properties there. So there is nothing special, but they are very useful in our arguments. Now, let's go back and look at some of the concepts in more detail. In OBJ specification languages, there are three kinds of top-level entities. These three kinds are objects, which can encapsulate executable code; theories. A theory defines properties that may or may not be satisfied by another object or theory; and views. A view is a binding of the entities declared in the theory. And objects and theories are called modules. So the three top-level entities in the OBJ specification are object, theories, and views. Objects are the ones which have the executable code in it. A theory is where the axioms reside, and we basically give properties. We specify certain properties, and these properties may or may not be satisfied by any other object or a theory. And the third one is the binding, and that is the views. The views, they bind these theories and objects with other theories and objects. So these are our three top-level components in an OBJ specification language. The first two, that is the object and the theory, they are known as modules. So what we have in an OBJ specification, we have the modules, and these modules, they are bound with the help of views. So this is what the general structure of our OBJ specification is going to be. Now, let me take you back to the slide and discuss it in more detail. Modules can import other modules. So we have the reuse as well as, it makes the hierarchy. We have the signature part, which defines a new sort. We can have variables with declared sorts. Terms are built up from variables and operators. Modules can be parameterized. Parameterized modules use theories to define both the syntax and semantics of their interfaces. And views indicate how to instantiate a parameterized module with an actual parameter. Like we saw in earlier algebraic specifications, we can import things. Here, in the case of OBJ specifications, once again, we have the notion of reuse and building the hierarchy, just like we did that in the case of other examples in our algebraic specifications. So that is the same as we saw earlier. We have the signature part, just like other algebraic specifications, and that signature part defines the sort that we are trying to build. We also have what is called parameterized modules. We have seen the examples of parameterized modules in the case of other algebraic specifications, when we built a list and tree and so on and so forth. This parameterized specification gives us the power of generically defining an abstract data type independent of the data that is stored in that abstract data type. For example, a list is a list. So you can have a list of integers, you can have a list of strings, you can have a list of other kinds of objects. So we define a list as a parameterized type, and then we specify the particular type that we need to use in a particular instance, just like we have templates in C++. So the concept of parameterized types is exactly like that. Rather, the concept of templates has come from the parameterized types in those specification languages that we had earlier, including OBJ itself. So we have the signature part and we have the parameterized types. And then we create the instances of those parameterized specifications in our OBJ specifications. So structurally, we are going to see different things, but conceptually, it is the same as what we have seen earlier. All the same components that we saw in other algebraic specification languages. Now, let's go back to the slide once again. The most important OBJ unit is the object, which encapsulates the executable code. Syntactically, an object begins with the keyword OBJ, all lowercase letters, and ends with end O. Once again, all lowercase letters. The name of the object occurs immediately after the OBJ keyword. Following this comes is, and then the body of the object. So here is a shell example. So we have this OBJ within these angle brackets, less than and greater than signs. We have mod id is, and then we have ... which is basically the body, and it ends with end O. For parameterized objects, the name is a simple identifier such as stack of int, phrase, or obj14. Parameterized objects have an interface specification in place of a simple name, and this we have mod id, that was the parameter type. Note one thing here, that this obj and end O, these are all lowercase keywords. They are written in all lowercase. So once again, nothing really very different and new, although the syntax is slightly different. So we define an object by saying obj and then giving it the name. It can be parameterized, followed by is, and then we have the body, and we terminate it with end O. So this is what our starting from obj to end O is what our object is. And the object is a module, and it encapsulates the executable code. So we can have executable code in the case of these modules here. Next comes what is a sort in the OBJ language. Once again, the idea of the sort is going to be very, very similar to what we have seen earlier. The only difference that you may see here is the syntax. It is slightly different syntax that we have. But the overall structure and idea remains the same. So I'm not going to go into too much detail here to explain what different things mean. I think you can easily make sense out of this thing. But let's look at it so that we understand what a sort is. A sort is declared with a syntax. We have sorts, and then we have sort ID list. So we can have more than one sorts declared in one go. So we, for example, here in this case, we have the sort ID list. So we can have sorts of NAT, which is natural number, INT, integer, RAT, rational numbers, and then a space and a full stop. So this declares these three sorts. If we have only one in the list, we can also write sort and then sort ID. For example, this is sort int and full stop. This sort is actually a special case of sorts, just a convenient way of writing when we have only one sort ID in the list. Otherwise, we could just simply write sorts and it could have only one element there also. So this sorts and sort, they are synonym, and there is no major difference here except that sorts can have more than one in the list and sort is going to have only one in the list. So the first thing that we do is we declare a sort. Note one thing here that this specification language is using two different keywords, sort and sorts, although they carry very similar meanings. So when we are declaring, we say that this is sorts and we provide a list of sorts that we will be using there. Or we can say only one sort, so we simply say sort, singular form, and then we provide only one ID, but there is no real difference in both these cases. And so with this, we have declared a sort that we will be using in our specifications. Now let us look at the order sorted algebra, OSA. It is designed to handle cases where things of one sort are also of another sort. For example, natural numbers are also integers. Where operators or expressions have several different sorts, provides subsort partial ordering among sorts, and it supports multiple inheritance. As I mentioned earlier in the beginning, OBJ specifications, they depend very heavily and they use what is known as sort order algebra, SOA. This sort order algebra basically lets us work with subtypes, so to speak. So if I have a natural number and there are certain properties that I have defined for natural numbers, then the same properties I can use with integers. There may be certain restrictions, there may be certain things which integers have and the natural numbers they do not. For example, we have negative numbers in the case of integers, but natural numbers that are not negative, and hence certain operations such as subtraction, we need to be very careful in the case of natural numbers, because subtraction can give us a negative result, and a negative result is not among a natural number, so we have to be very careful about that. So from a closure point of view, we have to be careful and we have to see a function is used properly. Anyway, we shall discuss that in more detail a little later. So it lets us work with subsorts. So we define a sort and then we reuse that sort, and that is what the sort order algebra is. That is, if we have defined something for one, and if it is using the same, then we can reuse it. So it is kind of an inheritance, and in the case of OBJ, it allows us to work with multiple inheritance. The sort order algebra also allows us to work with partial definitions. In abstract data types, we have this problem of partial specification, because we cannot specify all the exceptional cases and so on and so forth, and all the error conditions, and this sort order algebra lets us handle those kind of situations as well. but mainly it can be used to define inheritance hierarchies also, and then reuse what we have done for the base class, so to speak, and it can be used in the derived class. So the concept of object-oriented inheritance is very much there, and like I said earlier, a lot of these concepts were borrowed by the object-oriented programming language designers and were included in the programming languages, and hence the programming languages also benefited from the research in this area. Here is the example of a subsort. We have obj bits1 bits1 is sorts bits. So there are two sorts, one is bit and the other one is bits, and we are saying subsorts. Bit is a subsort of bits and we denote it with less than sign. So this is similar to saying that bit is a subset of bits. So less than is kind of subset. It actually means something very, very similar. And we have this OPS, two operations, 0 and 1, they give us bit. And then we have this op, and we are not defining op, but we are saying there is this op which can take a bit and bits, and it gives us bits. So here what we have said is, we have said this bit is a subset of bits. Bit is a type of bits. A single bit is a type of multiple bits. So multiple bits can have one or more bits. So we are defining two types, bit and bits, two sorts, bit and bits. And we are saying bit is a subset of bits. And then we specify operations on bits and bit, and the whole module is defined just like that. So we don't have to specify separate operations for bit, and we don't have to specify separate operation for bits. We say 0 and 1, they give us bit, a single bit. They don't give us bits. So this is also kind of saying that we have this bit which is either 0 or 1. So when we have only one bit, this is what we get. And the other operation is, equally supported on both these sorts, that is bit as well as bits. So we don't have to specify this operation again. In the case of, we don't have to say that this is the operation in the case of bit and this is the operation in the case of bits. As we have said, that since bit is a type of bits, is a subset of bits, is ordered less than bits, hence anything which is applicable on bits is also applicable on bit. So this is a very, very simple formulation that we have. Note one thing here, that anything which is applicable on bits is also applicable on bit, because a bit is a kind of bits. But it's not the other way around. Anything which is applicable on a bit is not applicable on bits. It is the same concept that we have in the case of inheritance. We inherit properties from the base class into the derived class, into the subclass. So all the operations that are defined in the base class, they are also available in the derived class, in the subclass, in the child class. But if we define a new operation in the child class, then that operation is not available in the base class. So this is basically the same concept that we have. But this gives us very powerful, very useful mechanism. See, we did not have to redo things again. In the other algebraic specification languages, we saw this thing. But there the mechanism was slightly different. But here the mechanism is very, very different. Now let us look at the equations and semantics. In OBJ specifications, semantics are of two types. Denotational semantics, which are based upon OSA, order sort algebra, and the operational semantics, which are based upon order sorted term rewriting. Now, we have two things here: denotational semantics and operational semantics. They are coming together. Denotational semantics, they are based upon the order sorted algebra. And the operational semantics, which are kind of executables, you actually execute and see what happens. They are based upon what is called order sorted term rewriting. Now, what does that mean? This order sorted term rewriting, we shall see in more detail a little later, but it uses equational algebra. Term rewriting means that given a term, can we replace this term with an equal term? So when we replace that term with an equal term, that is what rewriting means. So we have rewritten this term, and hence we try to simplify things, and we shall see in more detail. What we are going to do is we are going to give the recursive definition, something very, very similar to what we have in the case of induction. So we have the base step and we have the inductive step. So we will have that recursive definition there, and this term rewriting will be used there. So two types of semantics are given or can be given. One is the denotational semantics, which are logic terms, and then the operational semantics, which actually you execute by replacing terms with equal terms, and ultimately you reach your objective and verify whether something is satisfied or not satisfied. Semantics of an object are determined by its equations. Equations are written declaratively and interpreted operationally. So once again, these two things, denotational semantics and operational semantics here. We write the equations in denotational form, and they are executed in the operational form. And this is how we get the meaning, and this is how we verify things in our OBJ specification system. We rewrite rules, substitute instances of left side by corresponding substitution instances on the right side. So we have the equation. In the equation, remember, we have the left hand side and we have the right hand side of the equation. So we substitute the left hand side with the right hand side, and this is what the term rewriting is. This is the normal way of replacing equals with equals in our OBJ. But we can change this mechanism slightly, but I'm not going to go in that kind of detail here. But simply saying from left to right, replace the left hand side with the right hand side, and then we keep on working with that, and ultimately, hopefully, we will find the answer whether something is satisfied or not satisfied. Here is an example of an equation. We have this EQ m plus Sn is equal to S m plus n, S of m plus n, and then full stop. Here m and n are variables. This plus and S are operator symbols. EQ introduces the equation, and this equal separates the left and the right side of the equation. So in OBJ, when we write an equation, note one thing here, that this is an arithmetic equation. This is not an assignment statement in our programming language. This is an arithmetic or a logical equation in which the left hand side is supposed to be equal to the right hand side. So we write this equation, we say EQ. So when we have this EQ, small lowercase EQ, that starts the equation. And in the equation we have the left side, and then we have the equal sign, and then we have the other part, and at the end we have the full stop. So this equal separates the left hand side and the right hand side. In this particular example, these M and N, they were variables, and plus and S, they were operators. And these M and M, these were actually, this equation is for natural numbers, and we will probably use this equation somewhere ahead. And this M and N, these are two natural numbers, so we are saying M plus N. This S is the successor. So M plus successor of N is equal to successor of M plus N. So successor is the next natural number. So if I have 10, the successor of 10 is 11. The successor of 100 is 101, and so on and so forth. Successor is the next natural number in the sequence. So, but let's not get into what this really means and whether we can really prove that this actually works or not, but this is how we write equations in our OBJ specifications. So let us look at the operational semantics. We have this OBJ list of int is sort list, protecting int. This protecting int basically indicates that the int module for integers is imported. Subsort int is less than list. So the subsort declaration int less than list yields a syntax in which single integers such as 5 are valid lists. So we have op int list, which gives a list, op length list, which gives an integer, var I colon int dot var L colon list. So these are two variables. I is integer and L is list. Equation EQ length I is equal to 1. So when we have a single integer in the list, the length of the list is 1. And EQ length I L is equal to 1 plus length of L. So this is the recursive definition for the length. So when we have only one element in the list, the length is 1. If we have more than one elements in the list, then we say it is equal to the length of L minus 1 elements. If there were n elements, n minus 1 elements plus 1. The same recursive definition that we have seen earlier. We use the reduce command, which is executed by matching the given term with the left side of the equations and then replacing the matched subterm with the corresponding right side. This is called application of rewrite rules. The operational semantics for conditional rewrite rule is as follows. First, find a match for the left side, then evaluate the condition. After substituting the binding determined by the match, if it evaluates to true, then do the replacement by the right side. Again, using the values of the variable determined by the match. Note that evaluating the condition could require non-trivial further rewriting in some cases. So here is the example. We say reduce length 17 minus 4, 329. So the list is 3 integers, 17 minus 4 and 329. So we want to see, we say reduce and find the length. So when we do that, we say reduce in list of int, length 17, then it is reduced to -4, 329, and it says rewrites 5 and result nz nat 3. So this is the output that is generated. This is what happens here. We start with this length 17 -4, 329. It is reduced to 1 plus length -4, 329, which is reduced to 1 plus length 329, which is reduced to 1 plus 1 plus 1, which is reduced to 1 plus 2, and we finally get the answer 3, and this is what we call a trace of a computation. So here we specified a very simple sort, very simple module, and we evaluated that simple module. We say, okay, this is the scenario, this is the given, reduce it and try to find the value. Reduction basically means apply the rules, the equations that we have given earlier. Those equations, we will be using those equations. In that set, remember, we had two equations. The first equation was the base condition, which said if we had a list with only one integer there, the length of that list would be equal to 1. And the second rule was, that equation was that if we have a list, then we get the length by reducing the list one element at a time and adding 1 to the overall length of this structure. This is the same formulation that we have seen in earlier algebraic specifications. There is nothing new here. The only difference is a slight difference in the syntax. Obviously, it's a different language, so we have a different syntax. But formulation is exactly the same. But in this particular case, when we say reduce, the term rewriting is used, replacing equals with equals, left hand side with the right hand side, and we keep on applying this thing until we have a trivial base condition for which we know the answer. This is exactly what is done in Prolog programs. So this term rewriting is a very useful and very powerful concept, and actually lets us execute the specifications. This is how we build rapid prototypes in this particular case. So we write the specification and we also build the prototypes. We'll continue this discussion on OBJ family of specification languages in our next lecture, and we shall see in more detail some very interesting features of these languages. Until then, मुझे आप इजाज़त दीजिए. खुदा हाफ़िज़ और अस्सलाम वालेकुम.